Hello everyone, my name is Juraj Páleník, and together with my colleagues Thomas Sprengler and Helvig Hauser, we present the IsoTrotter, visually guided empirical modeling of atmospheric convection. Atmospheric convection is a process where warm air heated by the sun rises through the atmosphere. This process is responsible for moisture and energy transportation. It creates clouds and thunderstorms. In this example, we can see a convective process in water made visible by food coloring. A warm object was placed under the container to start the convective process. The study of atmospheric convection is a prominent field in metrology. It is almost exclusively studied by computational fluid dynamics. For example, in 2013, Miyamoto and colleagues attempted a global simulation of deep atmospheric convection. Even though they have used spatial resolution of less than 2 kilometers, they have not achieved convergence. While these simulations can be extremely useful, they are computationally expensive, difficult to analyze, and they do not provide simple answers to simple questions. Our goal is to come up with a simple model that will describe the properties of atmospheric convection. And if it fits reasonably well, we are able to learn something about the process itself. A simple model like this, verified by empirical data, can be used for forecasting or educational purposes. The empirical modeling, of course, comes with a set of challenges. The first challenge is to acquire sufficient empirical data that would enable the verification of the model. Secondly, the verification itself. It is especially difficult for models with many free parameters that can influence each other. Empirical modeling is, of course, not a new concept. Here we can see Galileo Galilei in the 16th century explaining the laws of gravity. He derived his laws from empirical observations of marbles rolling down an inclined plane. More recently, Thomas Mühlbacher and Harald Pieringer presented a framework for building and validating regression models. The major difference from our work is that we focus on parameter analysis of a model derived by the domain expert from the first principles, especially on the pairwise interaction between the parameters. The reason why this kind of work hasn't been done before is mostly due to the lack of measurements of atmospheric convection. While various kinds of meteorological observations are daily practice, there is no good way to measure atmospheric convection. This is mostly because the atmospheric convection is very localized, and one would need to release many sensors to acquire sufficient data. In order to circumvent this problem, we have decided to use people to measure the atmospheric convection. A group of people would jump from a tall mountain looking for atmospheric convection. This is called paragliding, and using a track log of such a flight, it is possible to locally reconstruct the strength of atmospheric convection. Here is an example of such a flight, where you can see a pilot rising up in the warm thermal air and then crossing over looking for another area of convection. Here's the whole flight seen from above. Here you can see 78 of such flights during a competition day. Collecting segments of tracks from the same location during a short time interval gives a reasonably good sampling of a single thermal. Our model of the atmospheric convection is one-dimensional, which means we are only interested in the vertical velocity of the air as a function of the altitude. The model itself is a set of differential equations that describes the strength of atmospheric convection. One can think of the core of our model as a bubble of warm air subject to the Archimedes law. As the bubble gains upwards speed, it is experiencing drag. And since the bubble is not enclosed, the warm air is mixing with the environment. We combine this computation with measurements of the environment to set the boundary conditions. In order to analyze and verify the behavior of the model, we've implemented a visual exploration tool. It consists of several parts. First one is the 3D view, where you can inspect the segmented thermals, and the analytical view, where the model can be analyzed. The model has 7 free parameters that the domain expert would adjust. The result of the model run can be seen on the left-hand side of the screen, and the parameters are also encoded in a domain-specific view, which shows the properties of the atmosphere. The list of segmented thermals can be found at the very bottom. Here you can see how adjusting the parameters affects the domain-specific view. In this example, increasing the temperature anomaly gives the thermal more energy, which corresponds to the increased red area in the domain-specific view. On the other hand, adjustment of the air temperature results in movement of the red area, having an immediate visual feedback for the effect of the parameters, not just on the resulting profile, but also on the intermediate computation, gave domain experts more insight into the working of the model. The blue and red intervals indicate behavior of the model under variation of the parameters. The information is used for sensitivity analysis and helps estimate the uncertainty of the model. We can notice the difference between the variation of the temperature anomaly and the air temperature. The biggest challenge was to estimate the joint effect of multiple parameters on the model. Without an interaction support, the user would have to simultaneously adjust two parameters, which did not lead to an efficient workflow. We've therefore introduced IsoTrotting. With IsoTrotting, the user can select a single point in the output space together with a bounds parameter. This bound parameter would be automatically adjusted by the tool such that the model always passes through the selected point. We call this point an anchor point, and an example can be seen here. The temperature anomaly was chosen as the bound parameter, and by adjusting the air temperature, a user can quickly understand the relationship between these two parameters. Now that we've seen a small example of the method, let's look deeper into how the method actually works. We define IsoTrotting for any scalar-valued model. It enables the user to explore the isosurface in the parameter space. The isosurface in the parameter space corresponds to a set of parameter values that results the same or similar outcome. The isosurface is explored by traversing along iso lines, effectively exploring the interplay of two parameters. On the illustration here, you can see the parameter variable space on the left, having temperature and pressure as the parameters and altitude as the variable. Model f is then a function assigning scalar-valued velocity for each point in the parameter variable space. Evaluating this function f at a single point corresponds to a single model run. Now, one can ask a very natural question, which is, which other parameter values will yield the same velocity? From the mathematical calculus, we know that all the points that give the same answer define an isosurface in the parameter variable space. In order to efficiently explore this isosurface, we propose to intersect with hyperplanes such that only an isoline remains, which can be very easily navigated. In this illustrative example, only a single hyperplane is necessary to obtain an isoline. The isoline is always located in a subspace defined by two parameters. From the computational view, the tracing of the isoline is achieved by varying a single parameter and solving for the other one. Let's now look at the results of the method. The first result includes a fundamental understanding of the workings of the model, where the domain experts were able to separate the effects of the air temperature and the temperature anomaly. From this finding, they were able to formulate hypotheses and propose a methodology for investigating the model parameters when compared with the real-world observations. The most important result of the IsoTrotting method is that it allows domain experts to rapidly investigate a combined behavior of two parameters. In this instance, it was discovered that increasing the drag would round the shape of the profile at the bottom. This behavior was then compared with the observed thermals. In conclusion, we presented a new empirical model of the atmospheric convection. We test and verify our model on a novel dataset compiled from the paragliding flights. In order to understand and verify the model, we presented novel visual parameter space analysis technique. We call this technique IsoTrotting and consider it applicable to any kind of scalar-valued model. The IsoTrotting enables the study of combined effects of two parameters, achieved by the exploration of the model's isostructures in the parameter space. In the future, we would like to improve the model by including the effects of the moisture on the atmospheric convection. The model itself can be used for forecasting the strength of the atmospheric convection, for educational purposes when explaining the properties of the atmospheric convection, and it could also be used as a subroutine in a more complex simulation. In the end, we would like to thank the Norwegian Airsport Federation for providing the paragliding data, Norwegian Meteorological Institute for providing the meteorological observations, and the anonymous reviewers for their valuable feedback. Fly safe.